My name is Adrian McGee, and this is my CS461 final project of 2025, Modern Object Detection for Self-Driving Cars from Sensors to Detection Models. The paper I'll be reading from is called All You Need for Object Detection from Pixels, Points, and Prompts to Next-Gen Fusion and Multimodal LLMs and VLMs in Autonomous Vehicles. By autonomous vehicles are rapidly transforming transportation, logistics, and agriculture, and public safety. Their performance depends on advanced AI systems that integrate perception, localization, planning, and control. Still, fully autonomous driving in complex, unpredictable environments remains unsolved. Challenges like urban chaos, bad weather, human behavior, edge cases, limited testing standards, and unclear regulations continue to slow widespread adoption. Solving these issues is critical for safe, reliable AV deployment. Adopting autonomous vehicles requires balancing safety, reliability, robustness, efficiency, accuracy, and scalability. Safety is the top concern, demanding consistent behavior, fail-safe mechanisms, and extensive testing. Reliability and robustness ensure AVs operate correctly even in noisy, harsh, or unexpected conditions. They must also react in real time, making split-second decisions to avoid collisions. High perception and localization accuracy enables AVs to detect objects, understand their position, and predict others' movements. Finally, efficient computing and energy use along with scalable systems that work across different vehicles and environments are essential for dependable deployment. Autonomous vehicles depend on large, diverse, and well-labeled datasets to perform reliably in real-world conditions. Models must see a wide range of scenarios including rare events, bad weather, and complex urban settings to generalize beyond control tests. Although multi-model data from cameras, LiDAR, and radar is essential, labeling it is time-consuming and limited by the rarity of high-risk edge cases. Synthetic data and augmentation help fill these gaps, but transferring synthetic knowledge to real-world environments remains difficult. Without representative data, models can become biased or unreliable, making scalable and adaptable data pipelines crucial for real-world deployment. Autonomous vehicles use a variety of sensors to understand their surroundings. Cameras capture visual detail, LiDAR provides 3D depth, radar works well in poor visibility, and ultrasonic sensors detect close obstacles. These are supported by HD maps and V2X communication, which share traffic and positioning information for better awareness. AVs also rely on internal sources like GPS, MIUs, and wheel odometry for accurate localization. Autonomous vehicles use advanced perception algorithms to interpret sensor data and understand their environment. These systems handle object detection, classification, segmentation, and motion prediction using 2D vision models, 3D LiDAR methods, and fused 2D, 3D approaches. Deep learning models like CNNs and transformers power real-time detection and scene understanding. Sensor fusion further boosts accuracy and robustness by integrating diverse sensor inputs using probabilistic methods and deep networks, enabling reliable real-time performance. Autonomous vehicles use two main types of sensors: proprioceptive sensors that measure the vehicle's internal state, like IMUs and GPS, and exteroceptive sensors that observe the outside world, such as cameras, LiDAR, radar, and ultrasonic sensors. These sensors can also be passive, relying on ambient signals, or active, emitting energy and analyzing its return. The survey compares these sensors types by performance and placement with a focus of external sensing since it's critical for perception. Understanding how each sensor works and its strengths and limitations is essential for accurate and reliable autonomous driving. Here is a table for criteria for each camera type. For example, we have lateral resolution is measured by pixels. For camera, it's very high, ultrasonic is very low, LiDAR is high, and radar is low. And this is just a comparison of all the criteria for each of the cameras. Autonomous vehicles use several types of cameras for perception, monocular, stereo, depth, and thermal. Monocular cameras are low cost and high resolution but lack depth and struggle with lighting. Stereo cameras create 3D depth from two images but require careful calibration and heavy computation. Depth cameras actively measure distance and work well in low texture areas, though they have limited range and issues in strong sunlight. Thermal cameras detect heat for reliable night and fog visibility, but offer low resolution and fewer visual details. Each camera type has trade-offs, and the best choice depends on the AV's environment and tasks. Here's a table of the summary of advantages and disadvantages of the various types of camera sensors. Ultrasonic sensors measure short-range distance by sending out high-frequency sound waves and timing their echoes. They come in different range types and are typically placed in bumpers to support parking, blind spot detection, and low-speed obstacle avoidance. These sensors are inexpensive, work well in darkness, and are reliable up close. However, they have limited range, struggle at high speeds or in noisy environments, and can be affected by weather. Overall, they're ideal for short-range, low-speed perception tasks. LiDAR sensors play a major role in AV perception by emitting laser pulses and measuring their return time to create precise 3D point clouds. This gives vehicles detailed spatial information for mapping and object detection. LiDAR provides accurate distance sensing in all lighting and strong geometric detail, but it is costly and can be fragile, and generates large data volumes that require heavy processing. Here is a table of the summary of advantages and disadvantages of the various types of LiDAR sensors. Radar sensors help autonomous vehicles measure the distance and speed of the objects by sending out radio waves and analyzing their reflections. Typically mounted on bumpers, radar supports ADAS tasks from close-range maneuvers to high-speed highway monitoring. It performs well in poor weather, measures speeds accurately, and is cheaper than LiDAR. Its limitations include lower spatial resolution and occasional false detections, but radar remains a key, cost-effective sensing technology for AVs. Here is a table of the summary of the key features, advantages, and disadvantages of various radar sensor types. Sensor fusion is critical for autonomous vehicles because it blends data from multiple sensors to build a more accurate and reliable view of the environment. This requires knowing each sensor's strengths, properly calibrating and synchronizing them, and choosing the right fusion algorithms. A common use case is object detection, where radar, camera, and LiDAR data complement one another to improve accuracy. Fusion methods occur at three levels: low level, mid level, and high level, each offering different trade-offs in accuracy and computation. Overall, sensor fusion enables safer, more dependable AV navigation. Here is a table of the summary of sensor fusion methods categorized by processing level, highlighting their sensor pairs, complementary applications, as well as their pros and cons. Despite major progress, AV sensing and fusion still face significant challenges. Different sensors produce various resolutions, data formats, making integration difficult, and processing large multi-model datasets in real time is computationally heavy. Sensor limitations like cameras struggling with lighting or LiDAR and bad weather also reduce reliability. Fusion adds complexity by requiring precise calibration and synchronization. On top of that, many rare and complex scenarios are missing from training data, limiting how well models generalize in the real world. High-quality, diverse datasets are crucial for developing and evaluating AV perception and decision-making systems. Existing datasets differ in sensors, annotations, and collection methods, so researchers must select those match their specific task, like detection, tracking, or scene understanding. To organize this space, AV datasets are grouped into 7 categories: ego vehicle perception, roadside perception, V2L, V2V, V2I, V2X, and I2I. Each category represents a different sensing or communication framework, supporting a range of research needs across the autonomous driving ecosystem. Here is a summary and comparative analysis of the ego vehicle perception data in autonomous vehicles. The BBD100K, one of the largest and most diverse open datasets available for autonomous driving research. The video clips were captured from various cities across the United States, including San Francisco, Oakland, San Jose, and New York City. The video clips include over 1,000 hours of driving footage, 120 million frames, and GPS and IMU trajectory data for each video. The Zenseact open dataset was gathered over 2 years by 14 European nations from Sweden to Italy to include diverse road conditions and environmental settings. It was designed to address existing dataset limitations by offering extensive sensing capabilities and diverse geographical coverage, as well as supporting multiple research applications such as detection, tracking, segmentation, sensor fusion, and weather classification. The Panda set was collected by a Chrysler Pacifica minivan equipped with advanced sensors capturing data across urban environments in California, USA. The sensor suites include 6 cameras, a 360-degree spinning LiDAR, a forward-facing long-range LiDAR, a GPS unit, IMU sensors. It contains 28 object classes annotated with 3D bounding boxes, along with 37 semantic categories that provide point-level annotations. Object detection is a core component of autonomous vehicle perception, enabling the real-time identification of vehicles, pedestrians, cyclists, and obstacles necessary for safe navigation and planning. Advances in sensors, deep learning transformers, and emerging vision language models have significantly improved detection capabilities. Modern AV object detection methods generally fall into 4 categories: 2D camera-based detection, 3D LiDAR-based detection, 2D, 3D fusion approaches, and techniques leveraging large language or vision language models. Here's a table for object detection in autonomous vehicles. Autonomous vehicles object detection is divided into several major categories based on sensor input and model design. 2D camera-based detection uses RGB images with CNN models like Yellow V4 and faster RCNN transformer models like Dieter or hybrid approaches applied to monocular, stereo, or multi-view setups. 3D LiDAR-based detection analyzes point clouds using anchor-based and anchor-free methods such as second PV, RCNN, and 3D SSD. 2D, 3D fusion combines camera and LiDAR data through early, mid, or late fusion to boost robustness. New LLM, VLM-based methods integrate language understanding to support zero-shot detection, grounding, and more general semantic reasoning. Within 2D detection specifically, methods are broadly grouped into CNN-based, transformer-based, and hybrid architectures. These systems follow a general pipeline involving feature extraction, region proposal, and object classification/localization. CNNs excel at learning hierarchical spatial features, where transformers capture a long-range dependencies through self-attention. Hybrid models combine both strengths, improving robustness and accuracy in complex driving environments. Here we have a diagram of a CNN-based architecture and a transformer-based architecture. We see with the CNN-based architecture that the image goes through the dataset, then goes to a convolution layer, a pooling layer, a flatten layer, into a softmax, and then we finally get our output, versus the transformer, which also uses an image as dataset, goes through a convolution layer, a pooling layer, but no flatten layer compared to the CNN based. Goes to a transformer, then goes to a head function, and then goes to an output. Here are the methods of, here is a table of popular 2D methods. As we can see, from the year, the backbone of data sets it uses, and then with easy and medium and hards, these are specific data that's being entered into each method, and these are the performance for each of these methods. Here is Table 15, which is a comparative analysis of all the 3D object detection methods using the camera-based KITTI dataset. Here is Table 17, a comparative analysis of yellow-based detection methods using the camera-based KITTI dataset. 2D 3D fusion combines camera images and LiDAR point clouds to boost detection accuracy and robustness in autonomous driving. Cameras provide rich texture and color details while LiDAR adds precise depth and geometric structure. Fusing these models help overcome the weakness of using either sensor alone. Fusion can occur at different stages: early fusion with raw data, mid-level fusion with shared features, or late fusion at decision level, each offering different trade-offs in performance. And here's a table comparing 2D, 3D fusion detection methods that also use the LiDAR KITTI dataset. And here we have a final chart which ranks the 2D, 3D, and fusion detection methods as the top three. LLMs are becoming important in autonomous driving because they provide semantic understanding, contextual reasoning, and language-based insights that traditional vision models cannot. They can interpret sensor data, summarize scenes, and support planning and decision-making. Unlike standard CV models that rely on images, LLMs work with language, and VLMs combine both images text for richer, more complete scene interpretation. VLMs can describe images, answer visual questions, and retrieve relevant scenes from text queries. Their framework processes images and text inputs through separate encoders, then fuses the resulting features to enable joint visual language reasoning. Here is a multi-model fusion, which is using a text encoder and then an image encoder. They both combine together, and then they both create an output with object detection, image captioning, image matching, visual grounding, and image understanding. Here's a table comparing popular VLM-based models for autonomous driving. My chosen model to improve is LiDAR LLM. I chose to use LiDAR LLM model because it was fully implemented online and highlights how language models are now being used in autonomous driving. I included both the original and a simplified version since the original required special hardware. The simplified model works by encoding a LiDAR bird's eye view feature, map it to a compact vector, and feeding it into a lightweight transformer for text generation or reasoning. This LiDAR context vector is prepended to the text tokens, allowing the model to use geometric information during prediction. The original design always injected LiDAR features with equal influence, but the updated version adds a learnable gating mechanism that scales the LiDAR input based on its quality. This makes the model more adaptive and better at handling noisy or uncertain LiDAR scenes while keeping the architecture efficient. Here is the full code of LiDAR LLM. This code defines a LiDAR LLM adapter model that sets a language model use LiDAR's bird eye view features to generate and interpret text. The LiDAR data is first processed through a convolutional layers and angle-based embeddings, then passed into a Q-former model that extracts a compact set of meaningful features. These features are projected into LLAMA's hidden space and injected into each transformer's layer, so the LLM can use LiDAR's context during text prediction. However, this code cannot be run normally because it requires external modules from the original research repo, large pertain LLMA, and BERT checkpoints, a proper folder structure, GPU support, and real BEV LiDAR tensors. Without all of these components, the script won't run as a standalone program. So instead of being able to run the full length of code, I decided to try to create a simpler version. This code runs a very small model that lets LiDAR data influence language model text input. It works by taking a bird's eye view LiDAR grid and passing it through a tiny CNN to create a single feature vector. A learnable gating layer then decides how much the LiDAR information should affect the model. Next, the text input is turned into embeddings, and the LiDAR vector is added in front of a special context token. This combines a sequence is processed by a small transformer, which lets the model mix the LiDAR signal with the text. The final layer converts the transformer's output into vocabulary logits, letting the model generate or score text tokens. For generation, the model repeatedly predicts the next token based on the prompt, and the fixed LiDAR context, extending the step-by-step. The example code at the bottom creates a fake LiDAR data, feeds in a small prompt, and shows the model producing a sequence tokens ID. Here is the simplified version of the code, and here are some changes that I added, which is the learnable gate to control LiDAR influence, and then applying a learnable gate controls how much LiDAR affects the model gate. The gating layer was added to give the model control over how strongly the LiDAR features should influence the language model. In the original design, the LiDAR vector was always used at full strength, even when the LiDAR signal was noisy, unclear, or irrelevant to the text being generated. This could confuse the model or lead to worse predictions. By adding a learnable gate, the model can automatically adjust the importance of LiDAR data. This will create a more flexible and robust system. When LiDAR data is reliable, the gate keeps the signal strong. When LiDAR is noisy and unhelpful, the gate reduces its impact. After running the code, here we can see some of the generated token IDs from the tensor. This paper reviewed the key components that make autonomous vehicle systems possible, from sensing technologies like cameras, LiDAR, radar, and ultrasonic sensors to perception algorithms, fusion methods, and large-scale data pipelines. We also examined internal state estimation, V2X communication, and emerging tools such as vision language models that expanded a vehicle's reasoning abilities. While progress has been substantial, AV still face challenges with robustness, rare edge cases, harsh weather, computation, and data quality. Continued innovation in models, sensors, integration, strategies, and regulation is essential. Ultimately, successful AV deployment depends on aligning technological, environmental, and societal factors to create a safe, reliable, and trustworthy systems. Looking ahead, I believe AI will continue to reshape the world in ways we can't yet fully imagine. While some see it as a risky, Looking ahead, I believe AI will continue to reshape the world in ways we can't yet fully imagine. While some see it as risky, I view AI as a powerful tool that can enhance safety, accessibility, and human progress. Autonomous vehicles show this clearly, offering mobility not just for transportation services, but for people with disabilities, the elderly, and anyone facing mobility challenges. As AI becomes more capable and responsible, its potential for social good will grow. Inspired by this, I plan to work on AI-related projects to build my skills and contribute to meaningful innovation in the future. Thank you for listening, and that concludes my presentation.